second session of this workshop about learning foundations. So the organization of this session will be the same as before. We'll have five-minute talks and then a little bit of time for Q&A. So please do not hesitate to ask your questions on Slack or in the Zoom. And also I encourage the various speakers of this session to try to ask questions to each other. And we will start with Hong Kong Yang and Weinan Yi. So please share your screen. I guess Hong Kong Yang will be presenting his work. Yes.
Hi, can you see the screen?
Yes, we can see your screen and we can hear you. Perfect. So welcome to this session. And Hong Kong Yang will present his work about the bias potential model.
Okay, so hello everyone. In this lecture, we will discuss the generalization ability of machine learning models that estimate probability distributions. And this work is done in collaboration with Professor Weinan. Basically, the task is to estimate some unknown distribution given finite sample points. And we have well-known models such as the GANs, VE, and normalizing flows. The important question is how to explain the generalization ability of these models. There are two challenges. First, we have the curse of dimensionality. It is known that for all estimation algorithms, the worst case sample complexity grows exponentially with dimension. And the second challenge is memorization. So if training converges globally, then the learned distribution will converge to the empirical distribution, which means that the model simply memorizes the sample points and becomes trivial. Nevertheless, we can establish the following picture. Despite that the model eventually converges to memorization and suffers from the curse of dimensionality, there will be a time period when the model comes very close to the target distribution. Specifically, with early stopping, the generalization error will become dimension independent. So for simplicity, we consider a model called the bias potential model. The distribution is parameterized as a Boltzmann distribution with a potential function V and some underlying distribution P. We model the potential function V as a kernel function with an RKHS norm, and we train this model by gradient flow on the log likelihoods. So unsurprisingly, we can establish memorization. If training converges to some weak limits, then the limit must be the empirical distribution. It suggests that the curse of dimensionality could be inevitable in the long time limit. Okay, so however, we can show that good generalization can still be achieved. Our main result is that if we assume that the target distribution is also a Boltzmann distribution, then with high probability, the generalization error measured by KR divergence is bounded by those two terms, the training error and the generalization gap. As a corollary, if we choose the optimal early stopping time, then the generalization error will be on the order of n to the power of -1/4. Therefore, the model avoids the curse of dimensionality and enjoys a polynomial simple complexity. Finally, let me mention the insights behind this implicit regularization results. The mechanism is that function classes, such as kernel functions and neural networks, have small Rademacher complexity, which usually scales as the Monte Carlo rate of 1/√n. It follows that the loss landscape is insensitive to this sampling error, so that the training trajectories over the empirical loss and the population loss would stay very close. So we expect that this reasoning holds for distribution learning models in general, that their generalization ability can be attributed to the choice of their function classes. And specifically in our latest paper, we have applied this idea to the generative adversarial networks, and we encourage you to take a look. Okay, that's the end of my presentation. Thank you.
Thank you for your presentation, Hong Kong. So now we will switch to the second talk, highlight of the session. Hassan Pourmamudagababa, please.
Yes, thank you.
Yeah, I can hear you and see your screen. So Hassan will present his work with Jeff Phillips on the orientation preserving vectorized distance between curves.
Yes. Thank you. Hi, everyone, and welcome to my talk. I'm going to talk about an orientation preserving vectorized distance between curves, which is my joint work with Jeff Phillips, my advisor at University of Utah. Okay. Consider two trajectories with m waypoints. There are some popular distances like Hausdorff distance, but Hausdorff distance does not care about the orientation of curves, and its complexity is linear in M. However, there are some other distances like dynamic time wrapping or Fréchet distance that do preserve the orientation of curves, but their complexity is quadratic in M. So it means they are, when M is large, they are slow. So we're interested in a distance that is not only as fast as calculating dot products in Euclidean spaces, but also, and most importantly, it provides an embedding for curves in a Euclidean space that enables the use of machine learning algorithms. Towards this goal, we introduce sign list function as follows. For a landmark Q and a positive parameter sigma, and for a curve gamma, we define the VQ sigma function in this way, where the first part, which is in magenta, encodes the sign and distance by the inner product. And the second part, I mean the Gaussian part, is the smoothing decay. And so, for example, consider these two curves here, which are the same but with different directions. The VQ sigma function will assign a positive value for the left-hand one, but a negative value for the other. So it means it's preserving, it is an orientation preserving function. And this is a nice pictorial sense of view, which is encoded by positive negative values for a curve with sidedness. In fact, consider any point in the plane as a potential landmark, then the value it takes from the curve is color. Now we vectorize the VQ sigma function based on the set of landmarks to get a feature mapping VQ sigma on curves. And this is the biggest advantage of our work because it enables using machine learning algorithms on trajectory datasets. And now the orientation preserving distance between for two curves, gamma and gamma prime, is defined by just the normalized Euclidean distance between two embedded curves under VQ sigma feature mapping. And this is the previous work by Jeff Phillips and Ping Huan Tang had a version of this, but it didn't preserve the orientation of curves. So this our work is an extension of this work to an orientation preserving distance. There are some theorems which I'm only showing two of them, and they are about landmark and curve stability. In fact, under some mild conditions, we have these two inequalities, where the first one shows the continuity of VQ sigma function under perturbations of landmarks, and the second one shows the continuity of DQ sigma distance under perturbations of curves in terms of Fréchet distance. This one shows the Fréchet distance. And finally, about experiments, we observed that both signed and unsigned versions worked well in classification tasks. However, when the direction of curves is essential, the signed version worked better than the unsigned one. And that's all. Thank you.
Thank you. So now we will switch to the third presentation. Luca Saglietti, who will present on solvable models to analyze knowledge distillation.
Can you hear me? Can you hear me?
Yes, we can hear you, and we can see your screen. So.
Yeah. Okay. All right. So hello everyone. Today I'm happy to briefly present some work done in collaboration with Lenka Steporova at EPFL. In particular, the goal of this paper was to get a better theoretical understanding of knowledge distillation, which is a very popular transfer learning and compression technique employed in many state-of-the-art applications today. The basic learning setup for knowledge distillation is the following. We consider a typical supervised learning problem with a data set that defines a set of input-output associations to be learned. And the final goal in this approach is actually to train a moderately small learning model on the given task. But the problem is that even though the number of parameters of this model might be sufficient for perfectly memorizing the training set, in practice, it could be pretty hard to find a configuration which also generalizes very well, since the network is quite small. So the big idea in knowledge distillation is that we can start by training a larger neural network on the same task. As we increase the degree of parameterization of our model, the magic of deep learning can start to happen. So basically, both the algorithmic bias of SGD and the intrinsic regularization properties of large networks can start to kick in and allows us to reliably find a good configuration. So what we can do now is to exploit the work done by the larger neural network to try and train our smaller initial network. In particular, in addition to the hard labels provided with the dataset, we can also give access to the student to the pre-activation produced by the larger network, creating a teacher-student type of relationship between the models. And basically, the initial classification problem is mixed with a regression problem where the student tries to produce the same distribution as the teacher. So the goal was to understand why this works so well in getting a good generalization for the student. And since this is our statistical physics work, we had to make a lot of approaches, as Mark was mentioning. So the first one is on the data model, and we consider a very simple model. It's a Gaussian mixture, and we actually consider the unbalanced case where the number of points in each of the two clouds is different. And we also look at the high dimensional case. So both the number of points and the dimension of each data point is going to infinity, but we are keeping the ratio fixed in the order 1. And the other big modeling assumption is on the learning model. And for simplicity, we considered a linear classifier that is trained on the data through L2 regularized logistic regression. Not, however, that we wanted to retain a very crucial detail for modeling knowledge distillation. And so we inserted a mismatch between teacher and student model. What we did was considering a student that is only training a fraction of its weights, and the rest is set to 0 from the initial condition. So in this way, it is actually impossible for the student to perfectly match the distribution of the teacher, and we are avoiding the collapse of the teacher onto the student onto the teacher. And instead, distillation has to take place. So what we're left with is a two-level problem where first we have to train the teacher on the given data set, and then the student has to start his training on using both the labels and also the pre-activation produced by the teacher. And we can study this with statistical physics method by using some methods from disordered systems, and in particular the replica method. And a very similar computation was done many years ago by Franz and Parisi, and this is called as Franz-Parisi potential. So I'll skip completely the part where we look at the details of the computation because there's no time. And I just would like to mention a couple qualitative results. And the first one is that we found that knowledge distillation is actually able to reliably transfer the regularization properties from the teacher to the student. In particular, if you set the regularization level of the teacher in a way that it achieves a very good generalization, then automatically also the student will get to a very good generalization when it learns through knowledge distillation. The problem is that if now we actually use direct regularization also on the student, we cannot get any bigger improvement. We can only match this optimized performance directly on the student. So no magic in this case. However, what is more magical is that if we don't know the type of regularization employed by the teacher, and in our study, for example, we take the bias optimal teacher, the student who learns from the activations is actually outperforming any student directly trained on the data. And this performance is quite stunning because it gets very close to the optimal performance achieved in a bias optimal setting. So I think this is very neat way to show that transfer learning is very good if applied in deep learning, where many implicit mechanisms are at work and we don't know what's really going on, but we can exploit the actual final result. And with this, I'd like to thank you for your attention.
Thank you. So the next highlight will be by Ziyu Zhu.
Just a second.
So please share your screen.
I'm about to switch. No.
Thank you. So Ziyu Zhu will present his work on dynamic algorithms for online multipose testing with Aditya Ramdas. Please go ahead. I don't hear you yet, Ziyu.
Can you hear me now?
Yeah, now we can hear you.
Okay, awesome. Cool. Hi, everyone. I'm go by Neil. I'm a grad student at Carnegie Mellon. I'm here to talk about my joint work with Aditya Ramdas on dynamic algorithms for online multiple testing. So first, I'm going to talk about the problem of online multiple testing. So imagine we're a tech company and we're interested in figuring out what things we could change to our web page that could improve user engagement. So maybe we could have one hypothesis that changing the color could improve user engagement, maybe changing the amount of icons, maybe changing the style of our app. And our issue here is we're kind of testing a lot of different hypotheses, and we want to identify the hypotheses where the user engagement actually is positive, so that actually make a difference. So we call this kind of rejecting the non-null hypotheses, where non-null hypotheses are the ones where it's not the null, there's a change in user engagement, and we actually want to reject those, essentially find those. And the analogy in kind of scientific discovery is kind of making true discoveries where the null hypothesis is not true, and we actually want to reject those. So the formalization of the setting is we kind of get a hypothesis and we get an associated p-value from the resulting experiment. And then the algorithm, which is what we're designing, is going to output a threshold, alpha level. So this alpha level is what decides whether we reject the hypothesis or not. If the threshold is under, if the p-value is under the threshold, we reject. Otherwise, we don't reject. And we kind of do this to a stream of hypotheses and p-values, and that's kind of the online multiple testing nature. And kind of what's, I guess, the fact we use about these p-values is that if the hypothesis is null, the p-values are what's called super uniformly distributed, but we can essentially think of them as uniformly distributed between 0 and 1. So there's a chance they're small and there's an equal chance they're large. But on the other hand, if the hypothesis is not null, then the p-values are hopefully small. So they're more prone to being under a threshold, and they're more prone to being rejected. So here, essentially, smaller p-values give us more evidence against the null. So even though our goal is to reject all these non-null hypotheses, we want to control kind of the error metric, because of course we could backwardsly just reject every hypothesis, and then we've achieved our goal of rejecting all non-null hypotheses. So kind of the error metric we're interested in controlling is something called the false discovery proportion, or FDP. So this is the ratio of false discoveries at time k to the total number of discoveries, where false discoveries are kind of the null hypotheses we reject, as opposed to the non-null. So prior work kind of has looked at something called the FDR, or false discovery rate, which looks at the expectation of the false discovery proportion at all fixed times. But this doesn't really tell us if we could control this error metric. It doesn't really tell us maybe about the tail of the false discovery proportion. So we're interested in controlling something called the FDX, false discovery exceedance, where we look at this kind of time uniform bound, which is the probability that at any time step after this user chosen time, large K, that the false discovery proportion exceeds this threshold epsilon. And similarly, we're also interested in looking at this augmented form of the false discovery rate, where we're looking at these data-dependent stopping times. So for example, such a stopping time could be like the time of the fifth rejection, where we have to decide whether we stop or the time is dependent on kind of the data that comes before. So our work is about controlling these metrics at a fixed level. So our contributions fundamentally are, we have the first practically powerful algorithm with FDX control. There's some prior algorithms that have provable FDX control, but we show that in practice, they have very low power and don't outperform even like a Bonferroni correction. And second, we show the first method that provides FDR control at stopping times. And orthogonal to these two contributions, we also show this new dynamic algorithm for allocating the alpha values that improve the power of our algorithm over prior methods. So that's it. Thanks.
Thank you. So now we'll have the last presentation of this session. And please, Maria Seleznova, share your screen. Okay, so we have Maria Seleznova presenting our work, answering the question, can we trust neural tangent kernel theory? And this is going to work with Gita Kutinyok. Please go ahead.
Thank you. So I will start by giving a short introduction to the NTK theory. The NTK kernel is a kernel given by the inner product of the gradients of the output function of a neural network, denoted F here, with respect to the trainable parameters that are here. And in the NTK theory, there are two main results on the infinite width limit of this kernel. In particular, the NTK kernel is deterministic under random initialization and stays constant during training. And this allows us to write the gradient flow dynamics of the output function of a neural network as a matrix ODE with this constant matrix theta star, which is the same dynamics that the kernel regression has. And this dynamics allows analytical treatment. So we can study infinitely wide deep neural networks using the NTK theory. But when can we also really use these results to approximate the behavior of finitely wide real neural networks? So in our work, we address this question, and we start with studying when, dependent on the network's hyperparameters, such as depth L with M, and initialization hyperparameters sigma W and sigma B, the empirical NTK is deterministic or random at initialization. And to do so, we study this ratio of the second moment of the NTK elements to their squared expectation. Here in the graphs, you can see separately the results for ReLU and for sigmoid networks. And here the NTK is approximately deterministic only in the black area. You can also see that for deep networks, for both activations, there is this phase transition from from deterministic to random NTK as we increase the variance of the weights, and it happens everywhere in the vicinity of the green dashed line. So this green dashed line is in fact the theoretical border between vanishing and exploding gradients for wide networks. Then, if we also try to see when networks are constant or dynamic during training, we see that also for ReLU and sigmoid networks, there is the transition, and it also happens in the vicinity of the border between vanishing and exploding gradients. In our work, we'll also discuss what the NTK regime can tell us about generalization of neural networks in view of these empirical results. So this theorem gives an expression for the variance of the output function of a trained network. And this expression is somewhat complex, but what we can say analyzing it separately for vanishing and exploding gradients is that basically for exploding gradients at initialization, the variance is large and grows with depth, while for vanishing gradients, it's low and decreases with depth. But for these results to hold, we need these two conditions, that the NTK regime holds and also that the NTK matrix is well conditioned. So when do these results hold together, these assumptions? Turns out that they only hold for shallow networks. And this suggests the performance of shallow networks with low variance for vanishing gradients and high variance for exploding gradients, which also agrees with experiments. But in case of deep networks, in case of exploding gradients, the NTK is random and changes during training. But in case of vanishing gradients, the NTK is actually poorly conditioned. So small random or data-dependent changes can be very significant for performance of such networks. Therefore, we conclude that it is hard to analyze deep networks using the NTK theory, and probably new approaches are needed to do so. Thank you.
Thank you. So now we'll have a little bit of time for the Q&A. Actually, we have 25 minutes before the break. So I will start by reading the questions that have been asked in the chat. So Johan has a question for Hassan. So Hassan, who was presenting his work on orientation preserving vectorized distances between curves. And the question is whether you have a motivating example of a ML task that leverages your curve distance.
Sure, that's a good question. There are many applications. For example, this vectorization makes clustering trivial, for example, with k-means. Another one can be, for example, using this vectorization, KNN, I mean, k-nearest neighbor search will be very efficient using Euclidean libraries. And another one can be classification task, which mostly our experiments were done on most data sets about classifications, both binary or multi-class, for example. And in fact, using our featurization, you can use support vector machines or random forest or whatever algorithm you have, because the input now is only a vector of numbers. And when time is important when in fact it's in data. For example, if you want to distinguish if someone goes to work or going back from work, and you want to distinguish these two trajectories, then the sign will be very important. So that was a good question.
Thank you. In fact, I have an additional question for you. So we have these landmarks that these points you call Q in the definition of the embedding. How do you choose them? Are they random points, IID?
Yeah. In the experiments in this paper, we just used a random set of landmarks. So they worked well with random set, but we're working on an optimization problem that to optimize the place of landmarks in order to work better on classification tasks.
So in fact, when you use these landmarks, which are random IID points, it seems to me that what you're doing is a random feature approximation of a kernel embedding. And then in the end, if you take the distribution of all the Qs, like you take the limit of an infinite number of landmarks, you would get a definite deterministic kernel, right? Do you understand?
Yes.
Yeah.
That's right. Sure.
Okay. So that's an object that could be maybe analyzed theoretically, this deterministic limit, or is it something you have thought about?
Yeah. In fact, that's just a sketch of curves. We sketch the curves and then do whatever we can in machine learning tests. So that representation of curves in terms of vectors to enables us to use algorithms.
All right, thank you. So
You're welcome.
now the next question in the chat is for Hong Kong, the talk which was about the bias potential model. And the question is from Joanne, who was asking, could you comment on how your generalization memorization results compare with classic kernel density estimation?
Okay, sure. So in a way, so the modern models for estimating probability distributions should lie in between two extremes. So one extremes are the classical non-parametric methods, and one extreme are the classical parametric methods. So for the non-parametric methods, we have methods like histograms or kernel density estimators. So their feature is that they satisfy a universal approximation property, but their generalization error suffers from the curse of dimensionality. For the other extremes, like for the parametric methods, so usually we speak of the Gaussian families, and their property is that they have very good generalization error, so their simple complexity is only polynomial. Well, the issue is that those families are too restricted. So if we want to learn distributions such as the zeta by A or the distribution of natural images, we have to, in a way, we have to assume some kind of universal approximation. But one will also hope to have a polynomial simple complexity. So the difficulty is how to ensure both properties. And so far, so our results is so far the only result we know that satisfy both properties.
Okay. So
Sorry, can I follow up with maybe something? But in your results, there's an underlying assumption, right? That the energy function of the underlying distribution lives in a certain RKHS ball.
Yes.
So is this something that is kind of hiding the curse of dimensionality somehow? Because we can find, I mean, maybe the examples that would break, that would require a lot of samples for non-parametrics, they are precisely those where this energy is going to have a norm that can blow up potentially.
Well, it's not exactly RKHS ball, so it's okay that as long as the target potential function has a finite RKHS norm. And well, because those functions satisfy universal approximation property among continuous functions, we can show that those model distributions are also satisfy universal approximation among density functions with respect to the KL divergence. So I think it's a quite general assumption.
Thank you.
Thank you.
So I have another question for you, Hong Kong. So it seems to me that there is a link between the dynamics that you look at and the gradient flow and the unregularized logistic loss when you train a kernel machine, like for classification. Is that a link that you, I mean, is it just, I mean, is that something you have thought about, or am I wrong?
Yeah, I think the connection can be justified. So I've thought about applying this kind of analysis to regression with noise on the labels. So for that case, we can also show that, well, so the two trajectories, one for the population loss trajectory and the other for the noise corrupted one, will also stay very close in the beginning. So I think there should be something similar in that case.
Mm-hmm. Yeah, something like a classification task where in fact we have only labels, like positive labels. I mean, that rings, it seems to me that there are connections between the dynamics you look at and this, but yeah.
Yes, of course.
Something to explore. All right. So please again, do not hesitate to ask your questions and to react on the Q&A or on Slack. Otherwise, I will continue with my personal questions. Lucas Aglietti.
Sorry, can I just ask a question to Maria? It's not very precise, so apologies because maybe it's not a good question. But I was thinking when you see deviation from the NTK behavior in different networks, do you know how like it develops? Does it start like a local excitation somewhere in the network? Can the NTK be seen like a vacuum over which there are some type of excitation develop?
So if I understand you right, like you're asking if we know anything like to where it changes, because in the paper there is just the norm, right? So we only measure the norm, but in fact, yeah, there is something that we can say about how it changes, because, you know, so you can basically prove that it has, let's say, a close to diagonal structure in the beginning, like this diagonal part can be larger, like way larger, or not way larger than the non-diagonal blocks, but basically the diagonal elements of the kernel are always larger than the non-diagonal ones. And say if you consider a classification problem, well, where it moves in case of the successful training is to the structure where elements of the same class is just more correlated than elements of different classes. So in general, you know that all the gradients decrease during training. Like if you initialize it like without like very vanishing gradients. So in general, they decrease, but in terms of structure, it moves to correlated samples more and decorrelating other ones, which is like feature learning. But yeah, there's not much precise stuff about it as far as I know.
Thanks.
So I have another question for Maria. So if I understand correctly, you show that for deep neural networks, the two conditions for training in the NTK regime cannot hold simultaneously, like the fact that we have a deterministic kernel at initialization, and then that the smallest eigenvalue is not too small. But it seems to me that you do not answer what's happening exactly at the edge of chaos. So when we are not in the chaotic regime or in the other regime, as the variance is too small, but really at the edge of chaos, do you have a specific like what happens in this regime when we are exactly on the green line? Do you have some comments about that?
So what we see in our work is that in the age of chaos precisely, the behavior is actually similar to what happens with exploding gradients. And also if you try to, like there are some papers about what happens in this case with theoretical NTK, right? Where the behavior is actually different right in the middle, but for us in the experiments, it was like with the exploding gradients. But also here, what I can say is that if we treat networks that are finite widths, we cannot really find the age of chaos precisely because age of chaos is computed in the limit, right? So every time we're either one way or another way, we don't know where the exact limit is. So probably when we just computed it for the theoretical age of chaos, maybe it's not the exact age of chaos. That's why we didn't see really this difference. Okay.
So a small question also about your experimental setting. What kind of data set are you using?
So there was MNIST, and then the NTK was just sampled on random subsets of it to see how to see if it depends on this. Because obviously the kernel is sampled on small things. And yeah, unfortunately, we didn't do it on a different set because it would be just harder to find a situation where we can train a simple model that will have good results there. Because we trained networks that reached good losses.
Okay, thank you. So maybe I have a question for Luca Seglietti. I was wondering, you presented a model where there was unbalancedness between the two classes. Is that something important? Because I'm not sure I saw something about it later in the results you've presented.
Yeah, I'm sorry, I really didn't have time to really explain why we chose that. So to go a bit more into details, basically, if you take a Gaussian mixture with balanced clusters, then L2 regularized logistic regression is able to get to the optimal performance directly. And if instead you take unbalanced clusters, there's no way that only the regularization can take you to that type of performance, and there's a gap. So here it was really easy to see whether knowledge distillation could help you over perform with respect to these L2 regularized devices, or if you were just limited by that type of performance. So it was just to have some range where this technique for training the device could help you get to a better performance than usual.
Okay. And also, I was wondering, you studied the case of the regularized logistic loss, and in the limit when lambda the regularization either for the original trained model or for the no, just for the original trained model, then if we take the regularization to 0, we would get a max margin classifier. So would you be able to make the statistical physics analysis also in this case of 0 regularization, or the kinds of tools you use break down?
Yeah, I mean, exactly 0 is not really possible, at least when you have a small data set. So when you're in the regime where the data is separable, putting 0 into the regularization would just not give you a well-defined problem. So I don't think we have any better way of dealing with that you usually have in maths. So we just take the limit of very small regularization, but exactly 0 cannot really be studied.
Okay. Thank you. So now we'll ask a few questions to Ziyu Zhu, who was presenting his work about the dynamic algorithms for online multiple testing. So I'm not quite familiar with the subject of online multiple testing. And maybe my first question would be, is there some link, or can we make links between the kind of analysis you make and the online optimization in general, online algorithms? Or these are totally different subjects?
Yeah, I think I'm honestly not too familiar with online algorithms, but I think they're kind of a different problem. It is kind of related, I think, how generally like the paradigm way to look at online multiple testing is kind of to take a betting view, because what happens with these algorithms, so there's actually some connections kind of in a sense to betting algorithms, but not quite, because the way your bets work out is a little different. But kind of the idea is like how all these algorithms are formulated is like you have some wealth, and basically having non-zero wealth is equivalent to keeping one of the error metrics I described as being controlled under a fixed level. So then it's like, okay, now it's a question of how do I spend this wealth? And then also, depending on the type of error metric you control, you actually gain wealth back on rejection. Because if you look at all of these error metrics, it's like, hey, it's like something divided by the number of rejections. So when you increase the denominator, naturally you're decreasing this error metric, which means you kind of have more you can put in the numerator, which that's kind of the notion of you can earn things back, wealth back on rejection. So that's kind of how the algorithms play out. It's like, how do I spend wealth in a way that it's kind of spread out over all my p-values and all my hypotheses, so I can reject a lot of them? And how can I make sure I don't run into a situation where I can essentially never reject anything? And it's called alpha death, because you run out of wealth and you just have no power after a certain time.
Okay. Also, just to understand how you derived your algorithm, so essentially compared to previous works, you have changed the criterion according to which that you want that was controlling the false discovery rate, I think.
Right.
Like instead of having a bound on the expectation, you want a high probability bound, right? And so it gives you a different algorithm because you have changed the criterion. Is that somehow how that proceeds? Okay.
Yeah, so I guess kind of how to upper bound the false FDR, all these metrics, is essentially you design this estimator. And then this estimator essentially gives you this ratio between something about the numerator and something about the denominator. So usually in the numerator, it has some term with alpha values. And hence outputting alpha values and large alpha values, which means you're more likely to reject, is like spending more wealth. And there's something in all these estimators, all the denominators have basically something with the number of rejections. So basically it's like this conversion mechanism where you say, hey, I have this metric I want to bound. How do I convert it to an upper bound empirical estimator, which is not based on the number of null rejections or false discoveries, because that's something we don't know. And then we can convert that estimator into this kind of wealth algorithm. And then there's kind of like on top of that, which is orthogonal to how you convert the estimator into how much wealth you're getting and spending, how to actually spend that wealth. So that's why there's also the dynamic part of our paper, which is orthogonal to how to convert and how to pick estimators, which we convert to wealth.
Okay, thank you. It was clear. So if anyone has any question to the speaker of this session, that's the moment to ask it.
Yeah. Otherwise, I think it's a good time to remind you that any questions can also come offline, right, in the Slack. And now I think we are heading toward our second break. No, sorry, we're heading to our break, and we are gonna, I guess, maybe I don't know. It's a good time to thank the chair, Lenaic and Rachel from the other session, as well as all the authors. Now, we can resume again in, I think it's in 25 minutes with the third session.
Thank you, Joanne, and thanks to the speakers.
Thank you, Lenaic.